In this week's lab, you're going to be selecting members for a steel truss. And some of those truss members are going to be under compression. So in this video, we're going to take a look at how we handle those kind of members. Now let's start by reviewing how columns fail. You did a lab in which you took dowel rods and placed them under compressive loads and found that the failure mode was buckling. That is, you begin to deflect sideways the rod, and it doesn't take any additional load to cause additional deflection. Now, if we're talking about steel, then if we have a very short column, then if we reach the yield strength before we reach the buckling strength, then the failure mode would be yield. So there's some cutoff between when we have yield and when we have buckling. Now what the design codes will do will be, first of all, to define the factors of safety, also to define that threshold between yielding and buckling, long and short columns. And in the case of some of them, particularly aluminum, actually looks at an intermediate length column. So they have different standards for short, intermediate, and long. The steel code that we're going to look at just divides things into short columns and long columns. So the AISC is the American Institute of Steel Construction. They publish a handbook that is the guidelines for designing steel structures. And the steel that we're going to look at, the most commonly used structural steel, it's got a yield strength of 36,000 psi and a modulus of 29 million psi, and that's A36 steel. Now, if we think about the theoretical failure envelope here, remember that we derived or developed our critical stress equation, that is the Euler buckling load expressed as stress. And that quantity in the denominator, KL over R, we called the slenderness ratio. Now, this buckling stress could be very high if the column's short, but in that case, we know that the column's yield strength becomes into play, so the stress cannot exceed the 36,000 psi yield strength. So if we try to plot that, here's the theoretical buckling stress. And as you can see, for low slenderness ratios, that number goes way above our 36,000 yield strength. So we have to add this line that says, hey, we can't exceed that either. So in theory, everything below those two curves would be safe. However, this doesn't account for any imperfections of the part and doesn't have any factor of safety. So let's talk a little bit about factor of safety. And what it really is there is to account for uncertainties. And there can be a lot of uncertainties in there. You can be not sure about the loading that's applied, what the strength of the material is, how the manufacturing is done, etc., or even your own analysis as to how accurate that is. And so depending on what you're doing, that factor of safety can be really variable. In the case of machine design, where you have machinery that can be subjected to a lot of forces that are harder to analyze and harder to characterize, as well as fatigue, that is, stresses that are applied many, many times over the life, then having a factor of safety 5 or 6 is not uncommon. On the other end of the scale, if you're designing aerospace structures, then you really couldn't have an airplane that flew if you used a real high factor of safety. So you use a lower factor of safety, but for that reason you have to control very tightly the quality of the materials, quality of the workmanship. The analysis of the structure has to be very good. And so with those eliminating a lot of the uncertainties, you can use a low factor of safety. Now, civil engineering structures, such as the truss we're going to design, tend to use relatively low factors of safety as well, because most of the time the loads, well, all the time the loads are pretty well defined. The weight of the members is a lot of the loading, and then there are standard loadings for designing a building with floor loadings, etc. So because there's not the big variability in loading that there would be in, say, machine design, again, these factors of safety 1.5 to 2 are written into the design code. So For short columns, the AISC code says the factor of safety is 1.67. That's for yielding. For buckling, because it is a lot more uncertainty involved, the factor of safety goes up to a value of 1.92. Now, remember this too, though, that that buckling stress only applies if you have linear elastic behavior. Now, when steel shapes are being manufactured, particularly like wide flange beams, those are hot rolled, and so you can end up having residual stresses after manufacturing. And those residual stresses can be as high as half of the yield strength. Now, if a member is under tension or even bending, that really doesn't bother us too much. A little bit of localized yielding will occur, and so that load distribution will take care of the fact that there are some residual stresses. In the case of buckling, however, if you have local yielding, that can cause the buckling strength to be reduced as well. So with that in mind, the code picks the critical value of the slenderness ratio, and it's based on the fact that the residual stresses can be half of the yield strength. So if that's the case, then we assume that yielding can occur when the applied stress is half of the yield strength, 18,000 psi in this case. And so we set that equal to our Euler buckling stress and solve that for the critical slenderness ratio. KLR with the subscript C means critical. So there's our equation here, and so what that separates is we say that the Euler buckling equation only applies for a slenderness ratio that's greater than this critical KL over R. Now for A36 steel, this is only dependent on the modulus and the strength, and so we come up with a value of 126.1. That's going to be a constant, and that's what we'll compare any other slenderness ratio to. If it's below this, it's a short column. If it's greater than this, it's a long column. And also within the code, though, they do specify that you should not use a slenderness ratio greater than 200 at all. So based on that, let's go back to our curve a little bit, starting with the theoretical buckling curve. And remember that our yield strength is at 36,000 psi. So if we take half of that and find the slenderness ratio that corresponds to that, that's the number we calculated as 126.1. So, excuse me, the long column, as we said, the Euler buckling stress applies above that slenderness ratio. And below that slenderness ratio, we have a parabolic curve fit there. So without any factors of safety applies, these are going to be the stresses that are allowed by the AISC code. And now we need to knock those down with the factors of safety. Now, so we said a long column gets a factor of safety of 1.92. We also said yielding is at 1.67. So in this range of the short column, the factor of safety is variable. It goes from 1.67 up to the 1.92 of the long column. So our allowable region now is down in this blue shaded region. The maximum stress, you can see for a very short column, is only 20-some thousand psi. Well, it's 21,600 actually, based on the factor of safety of 1.67. And as we move into higher and higher slenderness ratios, of course, our allowable becomes down as buckling becomes more of a concern. So here are the equations that we're going to use. First of all, the critical slenderness ratio is given by the equation here, but we only have to work that out one time. For AS36 steel, it's always going to be 126.1. Then we guess at a column shape and calculate its slenderness ratio. I've used the symbol R here to be a ratio of the slenderness ratio of the column we're looking at compared to the critical value. And if that value is less than 1, then we have a short column. And in that case, we have to calculate the factor of safety. And there's our equation for that. You can see it's based on the value of R. And at the very minimum, if R is close to 0, then our factor of safety is 5/3, 1.67. And if it's at the critical value, it'll end up being the 1.92, same that you see for long columns. Once you know the factor of safety, you can calculate the allowable by this formula, which is the equation of that parabola with the factor of safety applied. If R is greater than 1, then you have a long column. And in that case, as we said, the factor of safety is 1.92, which also corresponds to 23/12. And so our allowable there is just the Euler buckling stress with that 23/12 factor of safety built in. And finally, we didn't really mention tension members, but if a member is in tension, it doesn't matter what the length is, then the factor of safety is 1.67. But in all cases where you have compression, keep in mind that the slenderness ratio, according to code, has to be less than 200. So that kind of gives us some background information, and in the next video we'll look at the truss that we're going to be analyzing and talk about how to apply these equations.